Okay, the recording has started. So the objective of recording the class is just in case you cannot make it one day, you have the recording and you can see it. It's not, oh, the professor is recording, I can just go and walk. I don't mind the class, I see it after. No, this is not the idea. And unfortunately, I really don't like to record. I think it's forced me to be sitting in the chair. I don't like that. But we have been like that like for 3 semesters already. I hope this is the last one that we have to do that, and we can go back to our normal life, no? Which we miss a lot. Okay, how we are going to evaluate the course? Homework, 55%, exam, 10%, quizzes, 5%, and lab, 30%. Okay, we will have some lab that you will have to do. I can see that there is a lot of people. I'm surprised to see the number of people that we have. When we have lab, we will create a group of 2 people to do the lab. Okay, this is the course outline. So we will see a lot of topic. We will mostly cover all of them, but I never had time to cover all the topic because we go much slower than I would like. So maybe we cover it 70%. Okay, it will depend of the speed that we go. But this is the content of the course, and you can check it if you want. Do you have any question? No? It's clear for everybody? Okay, remember that you can participate. And this is what I was saying before. I would like you to participate. Let me take attendance. If your name is not in the list, please email me after the class and tell me that your name was not in the list. Now, this is the list that I found in Canvas, so it should be updated, no? So normally I call people by first name, but when we have several people that have the first name, I have to use first name and last name, so it is a little more clear. Kyle? Kyle is not here? To care? Peyton? William? Artes? Logan Driver? Bailey? Logan Grant? Graham? Hunter? Timothy? Natalie? Daniel? Stefan Littlefield? You?
I'm Steven.
Oh, okay. So Stefan Littlefield is not here? Ryan?
Here.
Caleb? Tyler? Taylor? Tiffany? Andrew Patton, yeah. Fanny? Andrew Pruitt? Random? Isaiah? Not here? Yeah, Isaiah. Alison? Not here? Paul? Stephanie? Stephen Thompson? John? Not here? Jeremy? Not here? Okay, so we are going to make a review on numbers because we will be using numbers a lot during the semester. So this is just conversion between different bases, like the binary base, the octal base, the hexadecimal base, and adding numbers, something that you saw in CS230, no? So you should be familiar with that. So the first exercise that we are going to do is we have some number in the decimal base like 56, and we want to convert them in binary. So I'm going to do the first example here as a reminder, because you should know how to do that. So let's say that I want to convert 56 in binary. What should I do? So there are several methods, no? There is a method where you know the power of 2, you know all the power of 2. So you try to write 52 as a sum of power of 2. 56, sorry. So 56 is 32. 32 is a power of 2, no? Plus 24. Let me write that like that first. So it's 32 plus, in 24 we have 16 plus 8. So those are power of 2. So at the end, I can write 32 is present, 16 is present, 8 is present in the sum, 4 is not present, which is another power of 2, 2 is not present, and 1 is not present. So this will be this one, the third one that we have here, then 0, 0, 0. So in binary, it will be like that. So this is the first method. And to say that it is in base 2, we can write like that. So 56 is 1, 1, 1, 0, 0, 0 in base 2. This is the first method. There is another method that you have seen in class where you do divisions. So let's try this method. So I'm going to use this is the symbol that you use, no? For division. This is the correct symbol for division? Yeah. Okay. We are going to do division by 2, successive division by 2. So 56 divided by 2 is what? 28. And the remainder is 0. So we are going to divide now 28 by 2. This will give me 14. And the remainder is 0. We are going to keep dividing. So we keep dividing until we arrive to a quotient of 0. So 14 divided by 2 is 7. And the remainder is 0. 7 divided by 2 is 3. And the remainder is 1. 3 divided by 2 is 1. And the remainder is 1. I keep going because the quotient is not 0. So 1 divided by 2 is 0. And the remainder is 1. And we stop here, no? Because we have a quotient of 0. So what we are going to write, we are going to write the remainder from the last remainder to the first remainder. So 56 will be 1, 1, 1, 0, 0, 0, as we find previously, no, in binary. So to say that it is in binary, we can put parentheses on a small 2, or we can do that. We could put a bear on top of the number and put a small 2. Okay, this is two ways to say that the number is in binary. Okay. Should we do the 905? So it will be the same thing, no? I'm just going to skip it, the 905. Let's go to another exercise. So this exercise says convert the following number from binary, which is base 2, to base 10. Okay, so let me report the number first. Let's see if I can put both of them so we can see both of them. Okay, I need this number. Which is, I have a number in binary 1 0 1 1 1 0 1 1 0 1. And this number is in binary. So I need to convert it to the decimal base. So you remember that the least significant bit is associated to 2 to the power of 0. This one is associated to 2 to the power of 1. This one is associated to 2 square. This one to 2 cube. This one to 2 to the power of 4. This one to 2 to the power of 6. This one to 2 to the power of 7, 8, 9, and the last one to 2 to the power of 10, no? So we can, let's say that this number, I call it x. We can say that x is 1, because we have this 1 here, times 2 to the power of 10. Plus, we have a 0 here, 0 times 2 to the power of 9. Okay, this value is associated to 2 to the power of 9, no? Plus, we have a 1 here, associated to 2 to the power of 8. Then we have a 1 here, associated to 2 to the power of 7. Then we have a 1 associated to 2 to the power of 6. Then to 2 to the power 0, 1, 2, 3, 4. Oh my God, no, nobody told me anything. This is not 6. This is 5. You see? You don't help me, and we have to redo it. This is recorded so bad. Okay, so this is 2 to the power of 5, 2 to the power of 6, 2 to the power of 7, 2 to the power of 8, and 2 to the power of 9. So here it's 9, here it's 8, 7, 6, and 5. So we have 1 times 2 to the power of 9, plus 0 times 2 to the power of 8, plus 1 times 2 to the power of 7, plus 1 times 2 to the power of 6, plus 1 times 2 to the power of 5, plus 0 times 2 to the power of 4, 0 times 2 to the power of 4, I continue here, plus 1 times 2 to the power of 3, 1 times 2 to the power of 3, plus 1 times 2 square, plus 0 times 2 to the power of 1, plus 1 times 2 to the power of 0. Okay, so x will be 2 to the power of 9 is 512. So 1 times 512 will be just 512. 0 times something, which is in this case 0 times 128 is 0. So I can just put plus 0. This is 256, sorry. 0 times 256 will be 0. 1 times 128, 2 to the power of 7 is 128, it will be 128, no? 2 to the 6, 2 to the power of 6 is 64. 1 times 64 will be 64. 2 to the 5 is 32. 1 times 32 will be 32. 2 to the 4 is 16. 16 times 0 will be 0. 2 to the 3 is 8. 8 times 1 will be 8. 2 squared will be 4. 4 times 1 will be 4. 2 to the power of 1 will be 2. 2 times 0 will be 0. 2 to the power of 0 will be 1. 1 times 1 will be 1. So I can say that x is 512 plus 128 plus 64 plus 32 plus 8 plus 4 plus 1. Okay, so you compute that and you have the result, no? Okay, let's do it maybe one time. So 8 plus 4 will be 12, 12 plus 1 will be 13, 13 plus 32 will be 15 plus 30, which is 45, no? So we have 45, or let me write 45 here, plus 45. Okay, 128 plus 64 will be 192. So it's 512. Okay, so 5 plus 2 will be 7. 7 plus 2 will be 9. 4 plus 9 will be 13. 13 plus 1 will be 14. So I have a carry of 1. 1 plus 1 will be 2. 2 plus 5 will be 7. So this is 749. Let me just verify it with a calculator to be sure that we didn't make any error. So here I'm going to click on binary to tell that I'm in base 1, in base 2, sorry. And I'm going to type the number 1 0 1 1 1 0 1 1 0 1. And the result is 749, as you can see here in base 10, no? Okay, that's fine. We didn't make any mistake. Okay, exercise 3. Convert the following number from decimal, which is base 10, to hexadecimal, which is base 16. So let's do 786. So I have 786. And this 786 is in base 10. Just to make it clear, I can do that, no? We're talking a number in base 10. And I want to put this number in base 16. So what should I do? We have several methods, no? We can divide by 16 until we reach a quotient of 0. So we can do this 786, or is this 786? Which one are you more familiar? The first one or the second one? The second. Okay, so 786 divided by 16. So maybe we use our calculator to do that. I'm going to use the scientific calculator. So 786 divided by 16. The quotient will be 49. And I need the remainder. So to get the remainder, we can use the mod that is there. So let's do 786 mod 16. And it's telling me that the remainder is 2. Okay, so I need to keep going because the quotient is not 0. It's 49. So I'm going to divide 49 by 16. And it's 3 times, no? 3 times 16 is 48. And the remainder is 1. The quotient is not 0, so I keep dividing by 16. It will give me 0, and the remainder will be 3. So it means that this number is, remember that we write the remainder from the last one to the first one, is 312 in base 16. We can verify it, no? Let's verify it. This is associated with 16 to the 0. This is associated with 16 to the power of 1 and 16 square, no? So 312 in base 16 will be 3 times 16 square plus 1 times 16 to the power of 1 plus 2 times 16 to the power of 0. And this will be 3 times 256 plus 1 times 16, which is 16, plus 2 times 1, which is 2. 3 times 6 is 18. 3 times 5 is 15 plus 1 will be 16. And 3 times 2 is 6 plus 1, 7. So it will be that. And this result, 8 plus 8 is 6, and there is a carry. 6 plus 1 is 8. So it's giving me 786. Okay, the original number. So it's correct, no? So here I've converted from decimal to hexadecimal, and I took the hexadecimal back to the decimal to be sure that there were no error in all the calculus that I did, no? Okay, exercise 4. Convert the following number from hexadecimal to decimal. We just did one. Let's do this one. 8FB0. So we have 8FB0, which is a number in hexadecimal. So we want it in decimal. It will be 8 times 16 to the power of 3. No? Remember, this one is associated to 16 to the power of 0. This one to 16 to the power of 1. This one to 16 square. And this one to 16 cube. So plus F. F is 15 times 16 square plus B. B is 11. 11 times 16 to the power of 1 plus 0 times 16 to the power of 0. No? So this will give me 8 times, okay, maybe we compute. Oh, this will be 4096, isn't it? Because 16, let me see, 16 to the 3 is 2 to the 4 to the 3. So 2 to the 12. So it will be 4096, correct. So 8 times 4096 plus 15 times 256 plus 11 times 16, 11 times 16 plus 0. So, okay, this one is, okay, I think we better take a calculator to do that. So if I take it, 8 times 4096 is 32,768. 15 times 256 is 3,840. So plus 3,840. This will be 16 plus 16, so it will be 671, 176. That's it. So we just had to add up those numbers together, and we will have the solution. So maybe we just use a calculator, no? We already have one of the three numbers, plus 176, plus 32,768. So the result is 36,000. Oh, I lost it. I have to redo it. So 32,768 plus 3,840 plus 176. Okay, this is the result, and I can verify it with the calculator. I'm going to go to the programmer calculator. I'm going to say that we start, for example, in hexadecimal, and the number is 8 F B 0, and it says that in hexadecimal, in decimal, it should be 36,784. Okay, which is the one that we did find, no? Okay, that's good. Let's see the next exercise. Okay, exercise 5. They give me a number in hexadecimal and they ask me to go to binary. So let's take this number, AF024. So if we have AF024 in base hexadecimal and I want it in binary. So I could convert this number in decimal and go from decimal to binary, but this will be a lot of work. So I'm not going to use this method. There is a method that is much straightforward. And this method say what? For each hexadecimal, you can associate 4 binary. There is a table for that, no? So let me remind you the table. 0 will be 40 in binary. 1 will be 0001. 2 will be 0010. 3 will be 0011. 4 will be 0100. 5 will be 0101. 6 0110. 7 will be 0111. 8 will be 1000. 9 will be 1001. Okay, I have not space. I'm going to continue here. Maybe better here. Okay, so 10, which is A, should put A. A will be 1010. B, which is 11, will be 1011. C, which is 12, will be 1100. D, which is 13, will be 1101. E, which is 14, will be 1110. And finally, F will be 1111. So I look, the first hexadecimal, it's A. So according to the table, I have to replace it with 1010, no? As you can see, A is 1010. Okay, then we have F. So F will be replaced with 1, 1, 1, 1. Then we have a 0. That will be replaced by 0, 0, 0, 0. Then we have a 2, 0, 0, 1, 0. And finally, we have a 4, 0, 1, 0, 0. So in binary, it will be this number. Okay? So it's straightforward. It's very easy to go from hexadecimal to binary and vice versa. Let's do another example of hexadecimal to binary. We will use that a lot. So here we have, for example, 59ABC77. Okay, so 5, 9, A, B, C, 7, 7. So 5 is 0, 1, 0, 1. 9 is 1, 0, 0, 1. A is 1, 0, 1, 0. B, 1, 0, 1, 1. C, 1, 1, 0, 0. 7, 0, 1, 1, 1. And 7, 0, 1, 1, 1. Okay, that will be the number in binary. Any question on it? Okay, now they give me a number in binary, and they ask me to go to base 16, which is the hexadecimal base. So, okay, this number, I better put it like that. Okay, so we have a number which is 1, 2, 3, 4, 5, 6, 1. 1, 2, 3, 4, 5, 6, 1. 1, 2, 3, 4, 0. Then we have 1, 0, 0. 1, 0, 0. 1, 0, 1. 0, 0, 1, 1. Okay, I have this number in binary, and I want to convert it in hexadecimal. What should I do?
Do the reverse of what you just did.
Exactly, I can do the reverse operation. So I need to create a group of 4 bits. For each group of 4 bits, I will replace the 4 bits with the hexadecimal equivalent. When I do the group of 4 bits, I have to make the group from right to left. Never do them from left to right. So I start on the right part of the number, and this will be the first group of 4 bits. Then there is another group of 4 bits. Then there is another group of 4 bits. Then there is another group of 4 bits, and the last group of 4 bits. So this group of 4 bits is 3. This one is 5. This one is 2. This one is C. This one is F. So the number, if I call the number X in hexadecimal will be FC253. Okay? Very fast to go, no? Let's do another example. Let's take this second example that is here. Let me put it here so I can report it. And we will see why it's important to do group from right to left, and we cannot do the other way. So the number is 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, and 0, 0, 0, 0. Okay, we have this number. Okay, so we are going to make groups starting on the right side of the number and going toward the left side. So this is the first group of 4 bits. Then we have another 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 group of 4 bits. And here, 4, 4, 4, 4. Here there is a bit that is alone. So since we need a group of 4 bits, what normally we do padding, left padding. So we can say that we can add to this number 3 zeros that are not significant, no? And we will have another group of 4 bits. So this one is 0, this one is B, 1010 is A, 0110 is 6, 1101 is D, and 001 is 1. So this is the number. If you have starting on the left side, you will have done padding here, and the number will be different. So it's why we have to start on the right side to write the left, no, to have the correct number. Of course, if you add 3 0 here, the number is not the same one. If I have a number x, and like for example this one, and I add a 0 at the end, what will be the relationship with between the initial number and the number with a 0 at the end? Let's say that if the initial number, I call it x. If this number, I call it x. And here to x, I add a 0. What will be the relationship between x and this number where I add a 0? Let's call this number, for example, y. What is the relationship between x and y? 2 times x, isn't it? 2 times x give me y. In decimal, every time that you add a 0 at the end, you multiply by 10. In binary, every time that you add a 0 at the end, you multiply by 2. So if you add 2 0, you multiply by 4. If you add 3 0 at the end of a number, you multiply by 8. Like in decimal, if you add 2 0, you multiply by 100. If you add 3 0, you multiply by 1000. Okay, that would be the decimal base. In binary, we are using power of 2. So we multiply by 2, or 4, or 8, or 16, or 32, which are the power of 2, no? Okay. In this question, we are working with 8 bit. Compute the 1 complement of the following binary number. The answer must be given on 8 bits. So how do we compute the 1 complement? What is the method to compute the 1 complement? We invert all the bits. So we change a 0 in a 1 and a 1 in a 0. This is the 1 complement. So look at this number. For me, it's a little difficult to memorize this number in binary. But if I put it in hexadecimal, it's FC. So I can just remember FC, and I can go to paint and put the number. So F is this, and C is this. So this is a value, let's call it X. And we want to compute the 1 complement of X. When we do the 1 complement, as I was telling you, we just need to invert each bit. So this one will become a 0, 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 a 0, a 0, a 1, and a 1. This will be the 1 complement. Okay, you invert each bit. You change a 0 in a 1 and a 1 in a 0. Let's take another example. For example, this one. In hexadecimal, this is what? This is B5, isn't it? So let's do B5. So let's call it Y. B is 1011. and 5 is 0, 1, 0, 1. So I want the 1 complement of y. So a 1 becomes a 0 become a 1, a 1 I change it to a 0, a 1 I change it to a 0 I change it to a 1, a 1 I change it to a 0 I change it to a 1, and a 1 I change it to a 0. So you just invert each bit and you get the 1 complement. Is it okay? You have seen all this in CS450, no? Okay, now we want to compute the 2 complement in exercise 8. So they give you a number and they ask you to compute the 2 complement. Let me take this number. This number is what in hexadecimal? Is A0. Okay? So let me clean the space to work. Let's call this number, for example, Z. And Z is A0. And I want to compute the 2 complement of Z. So we have 2 methods to compute the 2 complement of Z. We can do 1 complement of Z plus 1. This will be the 2 complement. So let's do the first method. What will be the 1 complement of Z? So if I invert this, I will have 0, 1, 0, 1, 1, 1, 1, 1. Okay, I just invert bit, all the bits of Z, no? Okay, I'm going to add 1. So if you are going to add 1, you are adding like that. This is 1. So let's add. 1 plus 1 is 1, 0. So I put 0 here and I have a carry of 1. 1 plus 1 plus 0 is 1, 0. I put a 0 here and I have a carry of 1. 1 plus 1 plus 0 is 1, 0. I put a 0 here, a carry of 1. 1 plus 1 plus 0 is 1, 0. 0 here, carry of 1. 1 plus 1 plus 0 will be also 1, 0. 0, carry of 1. 1 plus 0 is just 1. 1 plus 0 is 1, and 0 plus 0 is 0. This is the 2 complement. So this will be the 2 complement of the initial number, which is Z. So this is the first method. You do 1 complement plus 1, and you take the result over 8 bits. So the other method, let me show you the other method. Let me put the number again here. So the other methods say you parse the number from right to left and you split it in 2 parts. So the first part will include the first one. So here I split the number, I search the first one, and here is the first one. So I split after the first one. So the right part, you don't change it. On the left part, you do the 1 complement. So look at, this is Z, and I want to do the 2 complement of Z. So the right part, I don't change it. I keep it as it is. So I just copy it. On the left part, I change it. So this will give me the 2 complement. And as you can see, this number is the same as this number, no? 2 methods to have the 2 complement. The second method is easier. You just pass the number from right to left in search of the first one. You split the number in 2 parts. So the right part must include the first one. You keep the right part as it is. You don't change it. On the left part, you have to change it. Okay, you have to do the 1 complement of the left part. Let's do another example of 2 complement. For example, let's take this number. So this number is what? 9, 4. So let me clean everything. And I have a number that I'm going to call A. And A is 9. 4. Okay, I want to do the 2 complement of A. So first method is I do the 1 complement of A first. So if I invert all the bits here, I will have 0, 1, 1, 0, 1, 0, 1, 1. This is the 1 complement. I want to do plus 1. So I write here 1. This is 1. So 1 plus 1 is 1, 0. I put 0, I have a carry of 1. 1 plus 1 plus 0 is 1, 0. I have 0 here, I have a carry of 1. 1 plus 0 is just 1. 1 plus 0 is just 1. 0 plus 0 is just 0. 1 plus 0 is just 1. 1 plus 0 is just 1. And 0 plus 0 is just 0. That will be the 2 complement of A. So let's use the other method. I'm reporting A here, and I'm going to use the other method. So I'm going to parse the number from right to left in search of the first one. This is the first one. I split the number into parts. The right part must include the first one. Okay. I don't change the right part. So this is A, and this will be the 2 complement of A. I don't change the right part. I copy it as it is. And I invert the left part. So a 0 becomes a 1 becomes a 0 I change it to a 1, 0 is changed to a 1, and 1 is changed to a 0. So this number and this number must be the same one. Okay, because it's 2 methods to compute the 2 complements. Any question? Okay, let's see more exercise. Find the result of the following binary additions. Okay, let's do some additions. So let's put it here so we can see it. Let me clean the workspace. So we want to add 1, 1, 1, 1, 1, 1 with this number. So let me write them. 1, 1, 1, 1, 1, 1. And this number of 1, 2, 3, 4, 5, 6, 7, 8. So 1, 0, 0, 1, 0, 1, 1, 1. Of course, I have to align them, no? As we do in decimal. Okay, so 1 plus 1 is 1, 0. I put 0 here and I have a carry of 1. 1 plus 1 plus 1 is 1, 1, which is 3 in decimal. So I put a 1 here and I have a carry of 1. 1 plus 1 plus 1 is 1, 1. I put 1 here and I have a carry of 1. 1 plus 1 plus 0 is 1, 0. I put 0 here and I have a carry of 1. 1 plus 1 plus 1 is 1, 1. So I put a 1 here and I have a carry of 1. 1 plus 1 plus 0 is 1, 0. I put a 0 here and I have a carry of 1. 1 plus 0 is just 1. And 1. So this is the result. No? So what you need to know is that 1 plus 0, 0 plus 0 is 0, of course. 0 plus 1 is just 1. 1 plus 0 is just 1. 1 plus 1 is 2 in decimal, and in binary we will say 1, 0. So we put 0 in the column and we have a carry of 1. 1 plus 1 plus 1 is 3. And 3 is 1, 1. So we put 1 in the column and we have a carry of 1. We may have cases where we have 4, 1. So 4, 1 will be what? Will be 4, which is 1, 0, 0. So I put 0 and I have a carry of 1, 0, which means that in the next column, the carry is 0, so it doesn't matter. But the column that is more on the left than the next column, I have to put a carry of 1, no? Okay, let's do another additions. For example, let's do this one, C. So we have 3 numbers, as you can see, okay? So let me report the first number, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1. This is the first number in exercise C. Then we have another number, 1, 1, 0, 1, 0, 1, 1. Then we have a third number, which is 1, 1, 1, 0, 1, 1, 0, 1. Very important to align them well, no? So you are not confused with what you are doing. Okay, so can you help with that? Let me put it a little here. Okay, I'm going to use the red color to do the result. So here we have 1 plus 1 plus 1. This is 3 in decimal, and 3 is 1, 1. So 1 here in this column, and in the column that is on the left, there is a carry of 1. So 1 plus 0 plus 1 plus 1 will be 3. In decimal, 3 is 1, 1. So I put a 1 here, and there is a carry of 1. 1 plus 1 plus 1 is 3 again. 1 here, there is a carry of 1. 1 plus 1 plus 1 plus 0 is 3 again. 1 here, there is a carry of 1. 1 plus 0 plus 0 plus 1 is just 2. So 0 here and a carry of 1. So in this column, we have 1 plus 1 plus 1 plus 1, which is 4. So 4 is like that. So this 0, I put it here. And this one, I put it here. You understand why? Because this 0, I can put it here, but putting a 0 here don't change anything. The 0 that is in the middle will be here. This one will be here. And this 0 is in the column where I am. I'm in this column, no? In this moment. So I put 1, 0, 0. So I keep going. 0 plus 0 plus 1 plus 0 is just 1. Keep going. 1 plus 1 plus 1 is 1, 1, which is 3. So 1 here and a carry here. 1 plus 0 is just 1, and 1 is just 1. So this is the result of adding the 3 numbers, no? Okay, subtracting. Let's do exercise 11 better. Let us assume that you are using a 8-bit processor and the 2 complement to represent negative number. Give the representation of the following decimal number as the 8-bit result. and has a 2 hexadecimal digit result. Okay, so if we are using an 8-bit processor and we are going to represent positive and negative number, what will be the range of number that we can represent? It's an 8-bit processor. So the range of value that we can represent go from negative 128 to 127. If we use 8 bits. Okay? So they ask you to represent 33 in the computer. How is 33 going to be represented? So 33, we need to put it in binary first. It's 32 plus 1. So in binary, 32, 16 is not here, 8 is not here, 4 is not here, 1 is here. That will be 33, isn't it? So since the computer have 8 bits, I cannot just represent 33 over 5 bits. So the result in the computer will be, it will be stored as 0001, 0001. So what I did here, I did padding. I add 30 at the beginning.
There needs to be an extra 0.
Between the ones here?
Yes.
1, 2, 4, 8, 16. Oh, you're right. So it was not the correct result. I was missing a 0. Thank you for noting that. So this is the number in binary. So we'll have a small change here. We'll have a 1 here and a 0. So this is the way that the computer is going to represent it. By the way, in hexadecimal, it will be 2, 1. 2 times 16, which is 32. 32 plus 1 is 33. Okay? So this is the binary representation and the hexadecimal representation. Now, let's say you want to represent negative 120. Let's call this number x. Remember, the range is between negative 128 and 127. So I can represent negative 120. How do I proceed to represent negative 120? What should I do first? I represent 120. Then I do the 2 complement. Correct. Okay, so let's do the representation of the absolute value of x. The absolute value of x is 120. So in binary, it will be 64 plus what is left here, 56, isn't it? And 56 is 32 plus, let's see, 56 is 32 plus 24, isn't it? And 24 is 16 plus 8. Okay, so this is in binary, it will be 128 is not there, 64 is there, 32 is there, 16 is there, 8 is there, 4 is not there, 2 is not there, 1 is not there. That will be the number in binary for 120. Now, if I want x, which is negative this number, I have to do the 2 complement. So I'm going to do the 2 complement of this number. I need to do the 2 complement of the absolute value. The 2 complement of this number. So if I do the 2 complement of this number, how do I proceed? I can do the method that we saw. We go from right to left in search of the first one. Let me put it in red. So the first one is this one. So we split the number in two parts. On the right part include the first one. So we don't change the right part, but we invert the left part. So that will be X in the computer, which is 8, 8 in hexadecimal. I'm going to show you something of the window calculator. It can do that for us. So let me open it. And look, here you can say if you work with 1 byte, 2 byte, 4 byte. So look, byte. When it's a byte, you are working with 1 byte, which is 8 bits. When it's a word, you are working with 16 bits. When you say double word, you are working with 32 bits. And when you say quadruple word, you are working with 64 bits. So all the modern microprocessors that we have in computer, all those are 64 bits. Okay, some years ago, we used to have 8 bits. So since I'm going to work on 8 bits, I keep here bytes. And for example, we did a representation of 33, which is 2, 1 in hexadecimal. So let me put here 2, 1. Look at it, say that 2, 1 is 33. And the binary will be 0010, 0001. This is what we find. Okay? Now, negative 120 is 88. So let me clear this, and I'm going to type 88. Look at, I type 88, it shows 88, and here it shows negative 120. Okay? When I work with byte, I cannot type more than 2 hexadecimal. So for example, here I'm in hexadecimal, let me type 2, 5, and try to type a 6. It will not allow me. Why it does not allow me? Because it's too big. A byte is 2 hexadecimal. I cannot type a third hexadecimal because I'm working with a byte. Okay, a byte is 8 bits, which is 2 hexadecimal. Okay, let's do the representation. Let's do this exercise. In this exercise, we are working with an 8-bit processor, and some integer are in memory. And we have, for example, this integer, AF. We want to know what is the value of AF in decimal. So let's see how we do that. So we have in memory, we have AF. Let's call it X. So what is the value of X for us? So let's put that in binary first. 1, 0, 1, 0, which is A. 1, 1, 1, 1, which is F. Okay. To know if this number is positive or not, I look the first bit. If the first bit is a 1, this number is negative. This means that X is negative. So I need to compute the absolute value of X to get X. So what can I do to compute the absolute value of X? How do I get the absolute value of X? I do the 2 complement of X, no? If I do the 2 complement of X, I will get the absolute value of X. So let's do the 2 complement of X. So I parse this number from right to left in search of the first one. The first one is here. So I split at this level, isn't it? You split at this level. So you keep as it is the right part. So I keep the 1 as it is. On the left part, which has 7 bits, I'm going to change them. 0, 0, 0, 1, 0, 1, 0. This will be the absolute value of x. So this 128 is not there, 64 is there. 32 is not there, 16 is there in the sum. 8 is not there, 4 is not there, 2 is not there, but 1 is there. So the absolute value of x is 64 plus 16 plus 1. 64 plus 16 will be 80. 80 plus 1 will be 81. So what is x at the end? Negative 81. We knew that it was negative. We compute the absolute value, and it's negative 81. So let's verify that with the window calculator. So I am working in bytes. Let me clear everything, and I'm going to type AF. So first A, then F, and it's a negative 81, as you can see. So this number is negative 81. This is the way that the microprocessor will represent negative 81 in memory. Let's do another example. For example, let's do 7.3. In memory, we have a number that is 7.3, and we want to know what is the value in decimal. So let me call this number y, and it's in hexadecimal, it's 7.3, no? So in binary, it will be 0, 1, 1, 1, 0, 0, 1, 1. This is 7.3. So is this number positive or negative? It is positive because the first bit is 0. If the first bit is 0, the number is positive. It can be 0 also, no? But if the first bit is 1, the number is negative. So this number is positive. Y is positive. How do I get the value of y? I don't have to do the 2 complement. I do the 2 complement when I go from when the number is negative and I want the absolute value. Or when I have the absolute value and I want the negative of this absolute value. So I don't do the 2 complement. I just say that y will be what in this case? Y will be, okay, so 128 is not there. It's not in the sum. 64 is there. So 64 plus this one, say that 32 is there. This one, say that 16 is in the sum. This 0, say that 8 is not in the sum. This 0, say that 4 is not in the sum. This one, say that 2 is in the sum. And this last one, say that 1 is in the sum. So 64 plus 32 will be 96. 16 plus 2 will be 18. 18 plus 1 will be 19, no? So 6 plus 9 is 15, and I have a carry. So this is 115. So let's ask the window calculator to say the same thing, no? So let me clean what we have, and I'm going to type 7.3 while I'm in hexadecimal. I am in hexadecimal. Let me type 7.3. And it say that in decimal it will be 115. Okay? Let's do one more example. CA is in a position of memory in the computer, and I want to know what is CA for the computer. Let's call this number Z. So Z is CA in a microprocessor that have 16 bits. So C is 1, 1, 0, 0. A is 1, 0, 1, 0. So this is the number in binary. Is this number positive or negative? Negative. Why? Because the first bit is a 1. Since it's a negative number, I need to first compute its absolute value. To do that, I need to do its 2 complement. So let me write it again. This is the original number. Okay, and to do the 2 complement, I parse this number from right to left in search of the first one. Here is the first one. So I split the number here. And to get the 2 complement, I don't change the right part. I keep it as it is, 1, 0. And I change the left part. So 1, 0, 1, 1, 0, 0. This will be the absolute value of Z. So 128 is not there in the sum. 64 is not there. 32 is there. So 32 plus 16 is there. 8 is not there. 4 is there. 2 is there in the sum. And 1 is not there. So it will be 48 plus 6. And 48 plus 6 is 54. So this is absolute value of Z. So Z, which is negative, will be negative 54. So let's verify that with the calculator that CA will be negative 64 for us. So let me remove the number that it is in the calculator and let me type CA, and in hexadecimal it says negative 54, as you can see. Okay? Okay, now we are working with a 16-bit processor. So we bought a processor that is a little better. And we have those numbers. And I want to know what is the value of those numbers. So let's try it. It will be a little longer because we have 16 bits. So let's call the first number, for example, A. And we have F50C in hexadecimal, no? Which will be in binary 1, 1, 1, 1. Then 0, 1, 0, 1 for 5. Then 0, 0, 0, 0 for 0. And then 1, 1, 0, 0 for C. Is this number positive or negative? Negative, because it starts with a 1. So I need to do the 2 complement to get the absolute value. So I'm going to say, okay, let's first compute the absolute value. So absolute value of A will be the 2 complement of A. So I need to do the 2 complement of 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0. So I'm going to pass the number from right to left in search of the first one. Here is the first one. So I split the number here in 2 parts, the right part and the left part. So I don't change the right part. I keep it as it is. So let me just copy 1, 1, 0, 0. I keep the right part as it is. And I invert the left part. So here we have a 1, it's become a 0. 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0. So this is the absolute value of A. So what can I say? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1, 2024. This is 2048. So 2048 is present. This will be 1024, it's not there. This will be 512. 512 is present. This will be 256, not present. This will be 128. 128 is present. Then this will be what? 64 is present. Then this one will be 32. 32 is present. Then this one will be 16. Let me see. Yeah, 128, 64, 32, 16, correct. Then this one will be 8, not present. This one will be 4, present in the sum. This one will be 2, not present. This one will be 1, not present in the sum. So, okay, let's just use the calculator to do that. So let me go to the scientific calculator better. 2048 plus 512 plus 128 plus 64 plus 32 plus 16 plus 4. So we can see here what we have added up. So it's giving me 2804. So this is the absolute value of A. So A will be negative 2804. So how can I verify that in my calculator? So let me go to the programmer calculator. And I'm going to say, I'm not going to work with a byte, but a word. Here I'm with word, which means 16-bit long. And I'm going to type this number, F50C, why I'm in hexadecimal. So I put hexadecimal here, and I type F50C. And look at here, it says it's negative 2804. Now, of course, if you try to add one more digit, it will not allow you. Okay, because 16-bit is 4 hexadecimal. 8-bit is 2 hexadecimal. Of course, we can also verify it another way. Let me show you another way to verify it. So I can be in decimal. Here I'm in decimal. And I'm going to type this number. So 2804. But this is the absolute value. So now I'm going to hit negative, and it says F50C. F50C. Okay, so you can go from decimal to the representation in the computer of a 16-bit, or from the representation in the computer of a 16-bit to decimal. Okay, let's do exercise 15. So we want you to add hexadecimal number. Okay, let's have fun with that. So let's take, for example, exercise B. So in exercise B, you have to add 8, 3, B, B, plus 0, A, 0, 3. What can we do to do that? We can put them in binary, both of them, and add them up in binary and come back to hexadecimal. It's going to take a long time to do that. So we can just add them up in hexadecimal. So B plus 3, B is 11. 11 plus 3 will be what? 14. And 14 is what? D. So this is a D. Okay, B plus 0 will be B. Another way to do it, you count on your hand. So you have to add 3 to B in the first column here. So you say C, after B we have C, D, E. C. Oh, it's E. It's not D. C, D, E. Yeah, it's E. Thanks to God. We did both methods and we realized it was not correct, no? So B is 11. B plus 3 will be 11 plus 3 will be 14. Yeah, 14 is E, correct. Okay, A plus 3, we can say B, C, D. Or we can say 3 plus 10 is 13. And 13 is D. And A plus 0 is just 8. Okay, let's take the example of C. 7, 8, F4 plus 6D, F2. So 4 plus 2 is 6. F plus F, 15 plus 15 is 30. What can I say about 30? 30 is 16 plus 14. So it will be 1. And 14 is what? E, isn't it? So I put E here and have a carry of 1. A plus 1 is 9. 9 plus D, what is D? 13. So I have 9 plus 13. 9 plus 13 is what? 22. 22 is what? 16 plus 6, which is 1, 6. So I put 6 here and have a carry of 1. 1 plus 7 is 8. 8 plus 6 is 14. And 14 is E. So this is the result. Of course, you can try the calculator to do that. So let me put me in hexadecimal. Let me clear everything. So I want to add up 7, 8, F4 plus 6, D, F2. So the result is E6, E6, as you can see here, no? Do you have any question? Okay, thank you. I see you next week.